In this video, we discuss some important properties of linear transformations, and we'll talk about two subspaces, two vector spaces associated with a given linear transformation. So suppose L is a linear transformation from vector space V into vector space W. So let's denote by 0 sub V, the zero vector in V, and 0 sub W, the zero vector in W. Then, a linear transformation always sends the zero vector in the domain into the zero vector in the codomain. This property is usually used to prove that a given function between two vector spaces is not a linear transformation. Okay, so if a function does not send the zero vector in V into the zero vector in W, then automatically you can conclude that that function is not a linear transformation. So this is just a consequence, no, of the equivalent formulation for our definition of a linear transformation. Okay, so if you have a linear combination of vectors v1, v2 up to vk, then L of this sum or this linear combination is always equal to this linear combination in W. Okay, so you can take out the scalars, then compute images of the vectors involved, and then take scalar multiples, and then perform, lastly, vector additions. This should hold for all vectors in V and all scalars. Consequently, if you have a basis for V, then this second property implies that for any U in the domain, the image of that vector is completely determined by the images under L of the basis elements. Okay, so if U is an arbitrary element of V, then it is a linear combination of the basis elements. And then L of U is just the linear combination, no, of the images of V1 up to Vn by the scalars in this linear combination. To illustrate, consider the function L from R to itself given by the exponential function. This is different, no, from the example in the last video. In the last video, our codomain was R plus, the set of all positive real numbers. Okay, here our codomain is equal to the domain. So actually, this is not a linear transformation. And we can verify that by looking at the image under L of the zero vector in R. The zero vector in R, no, in the domain is the real zero number, the real number zero rather. So L of 0 is e to the 0 or 1. This is the image of the zero vector in the domain. But in the codomain, the zero vector is the real number 0. So we see that L of 0 is not 0, showing that L is not a linear transformation. So here we illustrate property 3. Suppose L is a linear transformation from R2 to itself that sends the basis element 1, 0 to the vector 2, 1, and the basis element 0, 1 to negative 3, 2. Okay, recall that 1, 0 and 0, 1 forms a basis for the domain. So property 3 tells us that in order to obtain the image under L of an arbitrary vector in the domain, we can just express it as a linear combination of the basis vectors and then use these definitions for the images. So for instance, if you want to find the image under L of 2, 4, we just write 2, 4 as a linear combination of 1, 0, and 0, 1. So 2, 4 is the vector sum 2 times 1, 0 plus 4 times 0, 1. And because L is a linear transformation, this is just 2 times 1, 0, or rather 2 times L of 1, 0 plus 4 times L of 0, 1. Then you just apply the definition indicated for L about the images of the basis elements. So this thing here is equal to 2 times L of 1, 0 to 1 plus 4 times L of 0, 1, negative 3, 2. And you can just perform the vector operations on R2 to arrive at the final answer. So now we talk about one important subspace or vector space associated with a linear transformation. That is the kernel of the linear transformation. Given a linear transformation L from V into W, we define the kernel of L, denoted in this manner, to be the subset of the domain, which consists of vectors that is mapped into the zero vector in W. Okay, so these are the vectors that are sent by L into the zero vector in W. That's what we call the kernel. To illustrate, let's consider the linear operator that we saw in the last video from R3 to R3, defined as follows. What is the kernel of L? So by definition, the kernel is the set of all vectors in the domain. So the vectors in the domain are 3 vectors, x, y, z, that is sent by L into the zero vector in the codomain. The zero vector in the codomain is the 3 vector with all components equal to 0. But L is defined in this manner, so you can write this defining expression for the kernel as the vector x plus z, x plus y, y minus z equals the zero vector. Okay, so you can see here that the elements of the kernel is the vectors in the solution space of this homogeneous linear system. So we solve this homogeneous linear system to obtain a complete description of the kernel. And we already know how to do that, because this matrix equation can be written as this matrix equation, 3 by 3 matrix of coefficients multiplied by the vector of x, y, z equal to the zero vector. Note that this system has infinitely many solutions given by x plus z equals 0, x plus y equals 0, y minus z equals 0. Or you can write that as y equals negative x, z equals negative x. And x is a free variable. Okay, in other words, the kernel of the linear operator is the set of all 3 vectors of the form x, negative x, negative x, y equals negative x, z equals negative x. And x is arbitrary. So every element in the kernel is the scalar multiple of the vector 1, negative 1, negative 1. So this is nothing but the span of this vector. In particular, we see that the kernel is a one-dimensional subspace of R3.